Welcome to NASA STEM EPDC Quick Bits Big Ideas in Science Content. NASA STEM Engagement and Educator Professional Development Collaborative provides NASA resources and STEM strategies for STEM engagement. In this series, we intend to reach educators, parents, and caregivers to quickly explain a specific big idea in STEM. We will introduce a NASA example of how this idea is applied in the real world. And finally, we will demonstrate step-by-step how to lead this activity at home or in the classroom with your students. You might invite your students to watch with you at that time. We invite you to join us as we learn more from our specialists. Let's get started.
Hello there. I'm Dr. Ann Weiss of NASA's Langley Research Center. In this Quick Bits episode featuring NASA's Orion Launch Abort Vehicle Mass Properties Activity, we'll explore center of gravity, a physical science big idea that affects us and the objects we use in our everyday lives. So what is center of gravity? Well, if you've ever played on a seesaw or supervised your students on one, then you and they have experienced its effects. Gravity results in all objects falling to the ground. But if you place two items on either side of a seesaw, like the ant and the elephant in this animation, what happens? That's right, only one item, the elephant, falls to the ground, while the ant goes flying into the air. The seesaw rotated around the pole in the ground at the midpoint. That pole serves as the seesaw's center of gravity, a point in space around which gravity acts. If the objects were the same size and mass, two elephants for example, then the seesaw would be balanced and not rotate. That balance and lack of rotation is what scientists and engineers aim for when they design objects. And for over 100 years, various projects here at Langley have depended on precise center of gravity measurements and calculations. Founded as our nation's first civilian aeronautical research facility in 1917, Langley is NASA's original field center. Our mission is to drive advances in aeronautics, science, technology, and space exploration for the benefit of all humankind. For example, Langley's aeronautics researchers have contributed to the design and wind tunnel testing of the X-59. This experimental plane demonstrates innovative technology that reduces supersonic booms to quiet thumps, paving the way for commercial supersonic flight over land that is currently prohibited. Imagine, one day we might be able to fly from New York to Los Angeles in half the time. However, the focus of this Center of Gravity Quick Bits video is Orion and development of the Launch Abort vehicle, one milestone in NASA's Artemis program that aims to take astronauts deeper into space than we've ever gone before. Langley's mass properties engineers played a key role in measuring and calculating Orion's center of gravity prior to the Ascent Abort 2 flight test in July of 2019. Like previous versions, Orion's launch abort system would safely pull the capsule and astronaut crew away from the Space Launch System (SLS) rocket if an emergency occurred during ascent. It is hoped that this launch abort system never has to be used during an actual mission, but its presence must still be added to the center of gravity calculations for the entire launch vehicle. It cannot be emphasized enough that Langley's contribution is but one component that must integrate seamlessly with a complex system developed by many different people across all 10 NASA centers. To further explain the big idea behind our center's role in projects like X-59 and Ascent Abort 2, I've invited one of Langley's senior lead engineers to explain how one can visually estimate an object's center of gravity.
I'm Melvin Farrelby, the Director of Systems Analysis and Advanced Concepts here at NASA Langley. Today, I'd like to talk about the center of gravity. The center of gravity is the average location of the weight of an object. So, in other words, it's a point in, on, or around an object where all the weight can be placed. Why is this important? It's because we can completely describe the motion of that object through space in terms of the movement of the object's center of gravity from one place to another, up, down, left, right, backwards, and forwards. So I have a couple of examples on how to sort of eyeball the center of gravity. So first I have a coaster. this coaster here. It's actually a piece of rock, sandstone, I think. If you take a look at it, it's a square. It's kind of uniform, so there's just as much weight on the left side as the right side, on the top as there is on the bottom. So if we're going to take the average of top, bottom, left, right, then the center of gravity should be somewhere in the middle of this coaster. I guess I ought to do that so that I can give a little shout out. But also, since this is a three-dimensional object, it has thickness. So again, left, right, top, bottom is still uniform. So you could say that the center of gravity is somewhere located in the middle of the thickness. So in this particular case, the center of gravity is inside this coaster in the middle of the square, pretty much halfway between the top and the bottom. So if you can eyeball the center of gravity with a square rock, it's easier to eyeball the center of gravity with a circular coin. Again, it doesn't matter what shape it is. It doesn't matter what it's made out of. This is made out of metal and it's got some paint on it. But again, with the circle, the average is right in the center of the circle, and the center of gravity would be somewhere in the halfway through the coin thickness. Now, a couple of more difficult things. This is a concept of a reusable Mars lander. And when we compute the center of gravity of this, the center of gravity is where this point is. And the reason why is because when you take the average of all of the weight, there's more weight down here because of the landing legs and engines. They have a lot of weight with them, and that biases the average when you take a look at all of the fuel and cargo that is in the forward part of the vehicle. For those of you who are fans of Star Trek, usually the movies, this is the USS Reliant. And the podium here is, it sits at the center of gravity of the Reliant, which is somewhere in a saucer section. But again, since it is sort of symmetric along an axis that is going top to bottom, then it's in the middle of the ship, somewhere inside the saucer section. So what does all of this have to do with an airplane? An airplane flies. We can describe the motion of the airplane by a center of gravity. So here, again, the airplane is sort of symmetric along this axis, longitudinal axis. So you can pretty much believe that the center of gravity is in the middle of the fuselage here. But now you're talking about tail and wings and engines, and then all of the passenger compartment. The center of gravity is probably somewhere between these two doors here. So, but it could be a 747, it could be a Cessna, it could be a military jet. As long as we know where the center of gravity is, then we can describe the jet's motion, we can describe all the forces that act upon the vehicle while it is in flight, or even when it's on the ground. So, in summary, the center of gravity is a point in space. It can be inside or outside of the object, that all the weight can be placed and the object's motion can be described.
Using a descriptive approach to visually estimate center of gravity, as Melvin Farabee just showed us, is great for introducing this physical science big idea to younger audiences or students for the first time. To review, Melvin showed us 5 examples in which he visually estimated the center of gravity for either uniform, symmetric objects, for example the sandstone coaster and metal NASA coin, or non-uniform objects that may be symmetric around just one axis, the Mars Concept Lander, USS Reliant, and Boeing 747 model. What objects in your classroom and home do you think you and your students could visually estimate the center of gravity for now? Feel free to pause this video and try it with your students. For more advanced teachers, students, and NASA mass properties engineers, however, physics equations are used to describe an object's center of gravity. While the instructional activity I will demonstrate shortly relies on the visual descriptive approach, this time-lapse video shows you how Langley Mass Properties engineers precisely measured Orion's center of gravity at our hangar on center. A special cradle had to be constructed so that the 11-foot by 16-foot, almost 23,000-pound replica of the capsule, called a boilerplate, could be rotated to various positions. Lasers were then used to collect data along the X, Y, and Z axes, which was used to calculate mathematically Orion's center of gravity to a point on the capsule no larger than a dime. Now, you may be wondering what could happen if center of gravity is measured incorrectly. Well, objects could unexpectedly rotate like a seesaw, just like this 747 airplane, or structures can begin to buckle if not reinforced properly according to center of gravity calculations, as shown along this 747's fuselage. At NASA STEM EPDC, we strive to emphasize culturally responsive teaching, that is, drawing upon students' lived experiences when presenting STEM content. Thus, one may not have much personal, direct knowledge of airplanes, rockets, and space capsules, but it is likely that one has ridden in a car, truck, or bus. If you've ever been in a moving vehicle that went around a corner too fast, or drove over uneven terrain to the point where it felt like the vehicle might roll over, then you know firsthand the importance of center of gravity, even if you didn't know the physical science term. And that leads to an important extension that could facilitate cross-curricular connections between today's big idea and the arts and social studies. All objects, actual and imagined, have a center of gravity. This illustration depicts a common motif found in some Native American and Hindu cultures, which explains that Mother Earth is carried through our universe on the back of great cosmic animals, such as turtles and elephants. Both the individual animals and the whole stack have a center of gravity, even if that is not what necessarily first comes to mind when looking at this picture. Combining STEM content with these cultural perspectives helps to reinforce students' learning while also showing them the interconnectedness of our human knowledge. All right, this would be a perfect time to invite your students to join you as I demonstrate today's big idea using the Orion Launch Abort Vehicle Mass Properties activity. This diagram gives you a brief overview of suggested materials and directions, so feel free to again pause the video here to look over everything before proceeding. Also, this would be a great place to ask your students to think of other situations from their everyday lives in which estimating and knowing an object's center of gravity would keep them safe.
All right, so what I'm going to do now is I'm going to show you the instructional activity. This is modeling the Orion Launch Abort system. The basic activity requires 4 things. You need a chenille stick or pipe cleaner. You need a craft stick or popsicle stick. We prefer the skinnier ones. I know there are ones that are a little bit wider, but we do recommend the skinnier one. And then paper clips. For this activity, I'm going to start out with just show you your basic wire paper clips. Okay? So what we typically do with the students is we ask them, okay, well, can I balance the popsicle stick on my finger? And the answer to that is no, although we tend to joke if they manage to be able to do it, we'll give them a prize. But if you do this a couple times, it should get the students to realize that that's not going to be enough to balance it. So we're going to take the chenille stem, the pipe cleaner, and we're going to make ourselves a replica of the Orion space capsule. So we recommend that you cross the pipe cleaner and the craft stick such that you make like a T, and then you take one end and you wrap it around once. And you want to make sure it's nice and tight, okay? So it looks something like this, and we joke, like a whisker on a cat or a whisker on a dog. So then you take the 2 ends and you bring them together, you cross them like so, and then you twist them. And so we say to the students, so it's like closing the capsule. The astronauts would greatly prefer that you close the door before you launch the rocket. Now, once you have it closed, and you're going to have to reshape it a little bit, but what you want to do is you want to make it any shape, doesn't matter. I'm going to make it sort of like an oval here, so it looks, or maybe just more like a circle, so it looks kind of like a lollipop, like this, okay? And the important thing is if you looked to it to the side, you don't want the pipe cleaner doing this. You want everything to be relatively straight up and down like this, okay? And so you can joke with the little ones that they've made now a lollipop. Now, you go ahead and you turn it right side up, and you ask the students again, can I balance it on my finger? And most times, the answer to that question will still be no. right? And so this is where we introduce the idea of the paper clips. So when you're finding the center of gravity or finding the center of mass on something, you want to make sure that the amount of mass on one end is roughly equal to the other end. And so we're going to use the paper clips just like NASA does. These represent the ballast blocks. And so NASA puts ballast blocks in various areas of the space capsule to make sure that the launch abort system and the capsule are balanced and won't do a tip over during launch. So you take the paper clips and you do it opposite of the craft stick. Now when you attach the paper clips, you can have them clipped on like this, or you can have them clipped on such as they're hanging like this. Okay? And we recommend between 3 and 4 paper clips, particularly if they're these regular office-sized paper clips. And you just latch them down here at the bottom. I'm going to do it such that they're just going to dangle at the bottom. And I'm going to first try this with 3. So, right? So then I'm going to go ahead and I'm going to do that. And so at this point, this is what you're after. You want to make sure that it balances roughly straight up and down. Now you may have some students say, well, it's not straight up and down, and that's okay for 2 reasons. One, most students are going to have maybe not a symmetrical shape on either side of the craft stick. And the other reason is that when we launch rockets, typically very soon after launch, you'll start to see that the rocket looks like it's sort of tilting. And this is because of the orbital mechanics of the rotation of the Earth adding to the motion of the rocket as it propels itself through the atmosphere into orbit. If a student is really set on making sure that their model is straight up and down, then you can do a couple of things. One, you can add, and in my case, you can add the 4th paper clip. Sometimes that will help because it's a little bit more mass on the opposite end, like so. All right, which, if that happens, it starts to tilt to one side. Just move the paper clips down towards the bottom here. Okay. And so at this point, it'll stay almost straight up and down. So that is the basic activity that we're demonstrating in this particular quick bit video. Second part of this that I want to bring your attention to is the fact that we find ourselves in rather unusual circumstances with the pandemic, with COVID-19. And so your students may be in a situation where they're in the classroom and you can get these materials, but then again, they might be at home and you're teaching them virtually. So I want to give you some ideas of how you might be able to adapt this activity in such a way that you can still do it, even if the student doesn't have craft sticks or pipe cleaners at home. And so what you can do is you can have them do sort of like a scavenger hunt. You can tell them, okay, I'm going to give you 5 minutes. I want you, with the help of your parents, to get something that is, like the craft stick, is relatively thin and is straight. Something that is pliable, like the pipe cleaners, and then something that you could use that you might be able to clip onto the bottom here. And so I did that before I started the video here, so I'll kind of show you some things. I pulled an old nail file. You'll notice that that's relatively similar to the craft stick, but maybe you don't want to do that. A pen will work just well. Even cotton swab or toothpicks. So anything that kind of has sort of that rimrod straight aspect to it would work well as a substitute for the craft stick. And of course, in engineering, sometimes we are constrained by the materials that are available to us. And so sometimes we can only use certain materials. We might want to use something else, but it's not available to us. In terms of the pliable part, I could only come up with a couple of things. Things like twist ties work. Okay, they're a little bit smaller, but they're pliable. I even got a piece of tin foil and I kind of scrunched it up in such a way that it looks kind of like a chenille stem pipe cleaner before I actually go ahead and use it. And then in terms of things to clip on, the paper clips, you can use, grab some hairpins from mom or grandma or something like that. So those might work as well. And so then you can actually go ahead and you can still do this activity in the context of, okay, I'm teaching my students virtually. So if you go ahead and you test this out, this also allows for some questioning about, okay, what materials work well why did we end up choosing a pipe cleaner, a craft stick, and paper clips for the basic activity. So you can have your students then go ahead, and by all means, these are not the only materials. They're just kind of some examples, but you would then go ahead and do sort of the same thing. So I'm going to try this with the pen and the tin foil here. So I'd go ahead and I'd wrap it around, and then I'd go ahead and I'd bring the two ends together, and you can see, you know, all right, it's a little bit more difficult to do this with the materials that are not actually the ones that are listed, but I can still make a capsule, I can still have a launch abort system, and I can still test the idea, okay? And same like what I had before I put the paper clips on, this isn't working too well. So let me grab some of these paper clips off of my model here, and we'll go ahead and put them on the tin foil. And, you know, sometimes when we do the engineering design process, we come up with solutions that work well but can be improved. And so this is also another reason why this activity is great, because you can have these students test these alternate materials that you might not necessarily use, and then ask them, okay, so how does this relate to the real world when engineers are designing, say, cars or trucks or airplanes, or in case of NASA, a spacecraft or a launch abort system. Okay, so I almost got these all on here. And if it falls off of your pen or your craft stick here, that's okay. Let's get those on there, and then we'll go ahead and put this back in and try to kind of make it tight around there. And let's go ahead and see how this particular model works. Okay, so obviously this one's not working too well, but that could be because I don't have enough paper clips on the bottom of this. So I might need to put some more paper clips. But you get the idea. This is something that allows the students to test. And we want to remind you here at NASA that just because, you know, we do something once doesn't necessarily mean that it works right off the bat first time. Sometimes a lot of times we have to go back to the drawing board and just kind of say, okay, that didn't work too well. So like at Langley and stuff like that, we do these tests so that by the time you actually see the rocket launch, you haven't seen all of the times that we had to go back and correct or improve upon something. So this is obviously maybe not the best material. Oh, wait. This is obviously not the best material, but it can get the point across, which is the center of balance, center of gravity. What is necessary to make sure that something doesn't tip over? Or in the case of the Orion space capsule, make sure that it doesn't tumble end over end as we attempt to launch astronauts.
Viewers who may want to learn more about today's big idea, center of gravity, are invited to explore the NASA STEM EPDC Educator Badge, Balancing Act, Spacecraft Mass Properties, or the various center of gravity resources created by NASA's Glenn Research Center. Additional information may be found in the box below this video.
Thanks for watching this NASA STEM EPDC Quick Bit. Don't forget to check out the description below for more information and links.